Hi everyone, welcome to Random Thoughts with Alex. In this video I'm going to talk about a simple calculation of pi using just Pythagoras theorem. The idea of this video came several months ago when I was looking at videos to watch, and I came across a video that was about the calculation of pi, and I believe it was going to use the Pythagoras theorem. I don't remember the exact video, I don't remember which one it was, but just by looking at the title and looking at the title screen, I tried to figure out what they were trying to do. I took a piece of paper, I did some calculations, tried to figure out what they were doing, and indeed I was able to calculate pi. So I don't know if that was actually what they were doing in the video, but it seemed like an interesting and fun calculation, and so I would like to talk about it. So let's start with Pythagoras' theorem. It says if we have a right triangle, then the square of the length of the hypotenuse, which we will call c squared, is the sum of the squares of the two sides adjacent to the right angle, a squared plus b squared. I think everybody knows that. So if we take a circle, what exactly is pi? Well, pi is the ratio between the circumference of the circle and the diameter of a circle. Or we can say it's the ratio between the length of an arc that covers half of the circle and the radius of that circle. So if we take a circle with a radius of 1, then that half arc, which covers an angle of 180 degrees, has a length of pi. So if we can calculate that, then we can calculate pi. What I'm going to do here, I'm going to say that the diameter of the circle is my first estimation, my roughest estimation of pi. That might not seem like it makes a lot of sense, but we will improve upon that estimation in different iterations. So I'm going to call this estimation pi naught. I'm also going to call it S naught, which is simply, it is the length of a line segment. So now we're going to try to improve that estimation with a first iteration. So what I do is I divide that angle of 180 degrees into two angles of 90 degrees, and with each angle I'm cut off the arc of the circle with a straight line. So essentially we get two triangles. They're both right triangles. They have a equals 1 and b equals 1, which means that c squared is 1 squared plus 1 squared is 2. So c is the square root of 2. We have two such line segments that approximate the arc. So we get that S1 is the square root of 2 and pi 1 is 2 times S1, which is 2.83. So we're getting closer to pi. Now we'll put that aside and we'll do a second iteration by taking that 90-degree angle and dividing it into two 45-degree angles. Again, each 45-degree angle is going to cut off a part of the circle, an arc of the circle, and we're going to approximate that arc by a straight line. Now from trigonometry we know that the height from this diameter to the point that intersects the circle, that height is the square root of 2 over 2, and the remainder here from the left hand side to the intersection is 1 minus the square root of 2 over 2. We can also prove that with Pythagoras' law. You can try that for yourself. It's not so difficult. But now, applying Pythagoras' law to those two sides, to this little triangle here on the side of the circle, allows us to calculate that c squared rather, the square of this hypotenuse, the arc section that we're looking for, is 2 minus the square root of 2. So c itself, the length itself, is the square root of 2 minus the square root of 2. And we have 4 such line segments that approximate half of the circle. So now pi, the length of the half of the circle, is 4 times the square root of 2 minus the square root of 2, which is 3.06. We're starting to get pretty close to pi. And we can go on and on like this, but it's going to get more and more complicated to figure out what these smaller and smaller line segments are. So we're going to need to systematize this method if we want to go in principle all the way to infinity without making things too complicated. So to systematize what we were doing, let's just take an isosceles triangle where the two equal sides have a length of 1. So essentially what we have two lines that are going to cut off a circle with a unit radius, and we connect the two intersections with the circle by a line section that approximates a small arc of a circle. We call that line segment Sn, and its length Sn, and that is, we assume that we've obtained that after n iterations. So from the knowledge of Sn, can we calculate the next iteration Sn plus 1? So for that we need to divide that isosceles triangle into two triangles, and we extend the line connecting the two a little bit, so we create two smaller isosceles triangles, each of them with two equal sides with a length of 1. So the part that traverses the original triangle, we'll call the length of that x, and the part that goes beyond the original triangle, we'll call that y. And by definition, x plus y must equal 1 because these are isosceles triangles. So x plus y equals 1. This is one important thing that we need. Furthermore, we have two triangles. We have this larger triangle here within the original larger triangle, which is a right triangle, which has adjacent sides with length x and length Sn over 2 and a hypotenuse of 1. So we apply Pythagoras law, x squared plus S1 over 2 squared equals 1. We can solve that for x, and we find that x equals the square root of 1 minus Sn over 2 squared. So we know the length of x. So if we can calculate y, then we know that x plus y is 1, then we find a relationship between Sn plus Sn and Sn plus 1. So let's take that smaller triangle that's sticking out of the original triangle, also a right triangle. We know that the sides are y and Sn over 2, so we square each of those, and the sum of these two squares must be the square of the hypotenuse, so the square of Sn plus 1. Again, we solve for y, and we get that y equals the square root of Sn plus 1 squared minus Sn over 2 squared. So we have an equation for x, we have an equation for y, and we know that the sum of those two must be equal to 1. So let's collect all this information here on the left side of the screen, and let's do substitution. So we substitute x and y into this equation, x plus y equals 1, and we get this larger equation. Now we need to solve that for Sn plus 1 as a function of Sn. So in order to do that, we will keep this second square root on the left hand side. We'll move that first square root to the right hand side. So we get the equation that's shown here now. We take the square of both sides. On the left hand side it's easy, the square cancels out the square root. On the right hand side it's more complicated. We get 1 squared minus a double product because there's a minus sign here, so they get 2 times the square root of 1 minus Sn over 2 squared. And then the last term is the square root squared, which just cancels out the square root. So what we see here, On the left hand side and on the right hand side we have this Sn over 2 squared that we can cancel out. So that means we simply have an equation for Sn plus 1 squared. So if we take the square root of both sides, we have an equation for Sn plus 1. And that equation is Sn plus 1 equals the square root of 2 minus 2 times the square root of 1 minus Sn over 2 squared. Great. So we have an iterative equation that will allow us to calculate the next line segment that cuts off a small arc of the circle based on the previous one. We also know that iteration number 0 gives us S0 equals 2. Iteration 1 is pi 1 equals 2 times that line segment S1. Pi 2, or second iteration for pi, is 4 times the length of the section S2. So to generalize that, we get that pi n will be 2 to the power of n times Sn. And for Sn we can calculate from the previous S with this iterative equation. And that's it. So now we can just keep calculating subsequent iterations, subsequent estimations of pi, and the result is shown here for the first 5 iterations. And we see after 5 iterations 2 to the power of n is 32. Sn is a little under 0.1, and when we multiply them we get 3.14. So we get 2 significant digits after the decimal point that are correct. So how far can we go with that? Well, we can't improve the accuracy indefinitely, at least not if we use the normal numbers that are used in Excel or in C++, for instance. But after 14 iterations, we find the highest accuracy. We see we have about 8 digits behind the decimal points that are correct, and we make an error of about 10 to the minus 9. After that, the error starts increasing and the number of significant digits that are correct decreases. So why is that? Well, there's a good reason for that, and that has to do with what we call rounding errors. So when you calculate numbers in Excel, they don't have an infinite accuracy or an infinite precision. They have a limited precision, around 15 significant digits, 15, 16 significant digits. And so when you're doing a lot of calculations, every time you make a small error because you're cutting off after 16 digits. And when you're doing a lot of iterative calculations, you can actually accumulate errors like this. And here is particularly important because that line segment that we're calculating is smaller and smaller and smaller, but our rounding error is not getting smaller, it's probably getting bigger. So relatively speaking, our error is getting bigger fast. So once we go to the calculation of pi, we take that small number with its rounding error and we multiply it by a number that is getting bigger and bigger and bigger. By the time we're at 17, we multiply it by 2 to the 17th, which is more than 100,000. So we're multiplying our error by 100,000, which in this case is on the order of 10 to the minus 7. Nevertheless, it's not a perfect method to calculate pi, but it's actually not a bad method at all. It gives you 8 to 9 significant digits, and with a method that is relatively straightforward, that doesn't require a lot of computation to get there. And what's really interesting in my opinion is we didn't actually need any trigonometry. We only used Pythagoras law to get there. So there it is. I hope you liked this video. If you do, please like and subscribe, and I'll see you in the next video.